Section 3 starts to give a lot of rules to make taking derivatives a lot easier. The first one we're going to look at today is the power rule. The power rule is going to tell us what to do when we just have a variable raised to a power, x to a power, and the shortcuts to deal with that. We'll also be looking at the sum and difference rules, which talks about when we're adding more than one term together. Okay, so first of all, if we think about the derivative of a constant function, if we just have a constant number in here, then our f of x would be c, so then f of x plus h would still be c, and f of x would be c because it doesn't change. And so when I plug that into my formula for a derivative, I'm just going to end up with a 0 every time. And so the derivative of every constant function is a 0 function. So if I have a function that says f of x is equal to 3, then I know that f prime of x, because there's no variable here, is always going to be 0. Basically, it's a horizontal line, and so we know that the slope of the derivative is 0. Now, if we want to find the derivatives of some of these monomials here, where we have just powers, we can also look at these using our definition of derivative. Now, we've done most of these, so I'll go through them very quickly, but if we plug in x plus h minus x, we remember that the x cancels out pretty much immediately, leaving us with h over h, which cancels out to 1. If I did x squared, again, when we multiply this out, the x squareds are going to end up canceling each other out. We'll have this little bit left over, which is going to leave us with, after we cancel out the h's, 2x. Same thing with the cubes, that the x cubed terms are going to cancel out each time, leaving us with some x squareds with h's. After the h's cancel out, the only term that we're going to be left with is the 3x squared. Now we should notice a pattern in that, where when we have x it becomes 1, when we had x squared it became 2x, and when we had x cubed it became 3x squared. So the power rule is saying that anytime I take a derivative, if we say x to the nth power, and we want to take the derivative of that, the rule that we're going to follow is we take whatever power we have and we make that the new coefficient, multiply it by x, and then we subtract 1 from our exponent. Let's go back and look at those. My power was 1, I move it out front to be a coefficient, and then I subtract my power, which was 1, now it's 0, which is just 1. The next one, if I take x squared, I bring the 2 out in front, and I subtract my exponent by 1, which would be 1. X cubed, bring the 3 down in front, subtract by 1, and we get 2. So a very important rule that we use pretty frequently. So let's just run through these very quickly. X, we saw that as 1. X, bring the 2 in front, subtract the exponent by 1. Bring the 3 out front, subtract the exponent by 1. 6 out front, subtract the exponent by 1. It doesn't matter how big this gets, you still subtract the exponent by 1. The next rule is the constant multiple rule. If we have something like x to the 5th, but it has a number in front of it, a constant multiple, what it's telling us then is if I want the derivative of this, I can just pull the 3 out and really just look at, focus on the derivative of x to the 5th. So here are a few examples. If I had 2x, basically I would pull the 2 out, I would think about the derivative of x, which, using the power rule, exponent of 1 would just be 1. The next one would be 3 times the derivative of x squared. Okay, we bring the 2 out in front, the exponent, subtract the exponent by 1, which gives us 1, and now we can simplify this to 6x. Okay, the next one, we can pull the 3 out. We then look at the derivative of x to the 12th. We use the exponent as a coefficient, and we take our exponent, subtract by 1, leaving us with 36 x to the 11th. That's the constant multiple rule. We also have a sum and difference rule. What this is telling us is if we're adding or subtracting different derivatives, we've got different parts here, what I can do is I can focus on individual derivatives one at a time. So I can think of this d dx of x cubed, we already saw that that's 3x squared. Then I have a plus sign, and I'll look now at this one, I look at each part individually. In this next example, we just have a long chain, so again it's just plus, plus, plus. We treat each part individually by applying that rule. Okay, so I'm looking at the derivative of x to the 4th here. Okay, and I just plug it in. looking at the derivative of 2x squared, 3/4. Notice they've got the minus here, and the 19 minus here. And so we take the derivative of each part and simplify it. Now you wouldn't normally write all of this out. I would be fine with you just taking that shortcut, skipping straight from this step down to this one. In this next example, we're going to use our power rule and sum and difference rule to find horizontal tangents. Now remember, horizontal tangents are where we're getting tangents whose slopes are 0, which means we're looking for where our derivative is equal to 0. We can do this completely algebraically. We can find it algebraically by finding our derivative using the rules or shortcuts we've had, taking that derivative and setting it equal to 0. So we'll take our derivative of this using our rules. We'll bring the exponent out front and subtract our exponent by 1. Next part, 2 times 8 will give us 16x. Our exponent goes down by 1. Then we have plus 2, the constant multiple. That's going to be 0, so we don't have to write it. Our next step then, we're going to look at how setting this equal to 0, because that's where our tangent lines are going to be horizontal when the derivative is 0. So 4x cubed minus 16x equal to 0. We can then factor this out. 4x times x squared minus 4, or 4x times x minus 2, x plus 2. Finding our horizontal tangents then will be at 0, 2, and negative 2. Another thing to look at is second and higher order derivatives. What we're talking about here is after we take a derivative, we can take a derivative of that derivative and we call it a second derivative. And then you could take a derivative of that, which would give you a third derivative. So we call these f would be our original function, so f prime would be our first derivative, f double prime would be our second derivative, f with 3 primes would be our third derivative. Now at some point it becomes too much to keep writing these prime markings, so we might start writing with Roman numerals, which is probably what we'll do, but we won't often go that far. So here's an example of taking multiple derivatives. If I want to take my first derivative, I think of this as y prime is 3x squared minus 2 times 5 is 10, subtract our exponent by 1, and then the 2 becomes 0. If I take my second derivative, so y double prime, so 2 times 3 is 6, x, I subtract my exponent by 1, my exponent is 1, so I keep the 10, subtract my exponent 0, the x is gone. Then I can take a third derivative with 3 primes. The derivative of that is 6, the 10 is gone, and if I take a fourth derivative, I guess I will just make 4 marks here, the derivative of this is going to be 0. And so eventually with a polynomial function, our derivative is eventually going to work down to 0. Not every function will do that, but polynomial functions will.